Hi, my name is Louise, and today we're going to learn about nonlinear quadratic systems. We will specifically be going over how to solve systems with a line and a circle, and a system with two parabolas. Our previous lesson explored linear quadratic systems, which was a system of a line and a parabola. Nonlinear systems are simply a set of two or more equations that share variables, where at least one of the equations is nonlinear. Even though it sounds funny, a linear quadratic system is technically also a nonlinear quadratic system. By the end of this lesson, you will be able to roughly graph a quadratic system, which you most likely already have experience with. You will also be able to solve a quadratic system containing a line and a circle, as well as learning how to check for solutions to quadratic systems using graphing, which we'll specifically do for a quadratic system with two parabolas. Let's start by solving this quadratic system. This system of equations includes a line and a circle. I always recommend graphing the system of equations before we start to solve it. In case you are having a hard time visualizing how to graph these equations, let's work through it. One clear giveaway that the top equation, x squared plus y squared equals 16, is a circle, is the fact that both x and y are squared. One of the easiest ways to graph it is to start by finding intercepts. If we set y is equal to 0 in this first equation, we get that x squared is equal to 16. Now, once again, remember, when taking the square root of both sides, we have to add a plus minus in front of our solution. So this means that there are actually two x-intercepts, an x is equal to 4 and an x is equal to negative 4. The same thing happens when you set x to 0. You get y squared is equal to 16. Taking the square root of both sides, you get that y is equal to plus minus 4. Therefore, our y-intercepts will be 0, 4 and 0, negative 4. And this completes our circle. Excuse my very rough drawing of a circle. So you probably already have practiced graphing linear equations, but let's go ahead and do it as well. In the equation y is equal to negative x plus 2, when we set x equal to 0, we get that y is equal to 2. So we know that when x is 0, y is equal to 2. So that means this line will intercept right here. When we set y equal to 0, we get that x is equal to 2. This means that we have an intercept right here. We will get a line that approximately looks like this. And we see that there will be two intercept points. Here we have our graph done a little more nicely, so let's go about actually solving a system. As you can see from the graph, there will be two solutions, just like we said. Similar to how we solve linear quadratic equations, we can use substitution to solve the system. Since the bottom linear equation is already nicely solved for y, we can go ahead and plug this into the top equation. We'll get that x squared plus negative x plus 2 squared, which remember we drew from our bottom equation, is equal to 16. Now let's continue on to isolate x by expanding the binomial x squared minus 4x plus 4, which is all equal to 16. Let's simplify further. We get 2x squared minus 4x, and then subtracting 16 from both sides, we will get negative 12 is equal to 0. To make it easier on ourselves, we can divide both sides by 2, and we will get x squared minus 2x minus 6 is equal to 0. Unfortunately, this doesn't nicely work into whole number answers, which we can already tell from our graph. So we'll have to plug this into the quadratic formula. A is 1, B is negative 2, and C is negative 6. So we will get 2 plus minus the square root of 4 minus 4 times negative 6 times 1, all divided by 2. If we simplify this, and we will get 2 plus minus the square root of 28 all over 2, which we know is equal to x. To simplify this further, we can actually pull a square out of this root 28, because root 28 is also equal to 4 times 7. And pulling that 4 out, we'll get that this is equal to 2 plus minus 2 root 7 all over 2 equal to x. And all of these 2's can cancel out to get our final answer of 1 plus minus the square root of 7 is equal to x. And in case you are interested in what that is like as a decimal, the answers are x is equal to 3.646 and x is equal to negative 1.646. Once again, we aren't quite done yet. Now I'm going to go ahead and erase this top work so we have a little bit more space to plug in our x values into the linear equation to get the corresponding y values. So we have the linear equation y is equal to negative x plus 2. And plugging in our x values, we will get the corresponding y values. And here we will get y is equal to 1.646 and y is equal to 3.646. So our final solutions are 3.646, 1.646, and negative 1.646, 3.646. The second type of system I will be going over today is a quadratic system with two parabolas. As a reminder, quadratic systems can have 0, 1, or 2 solutions, as we discussed in the previous lesson. And just as we did for the previous system, let's start by graphing to get a rough estimate of what these parabolas look like on the graph and what our potential solutions could be like. This top equation is in standard form, but it'll be a lot easier to graph by hand if we transform it into vertex form. To do so, we need to get a perfect square, and we can use x squared plus 2x to make one. So, if we have x squared plus 2x, what do we have to add to make this a perfect square? Well, if we add 1, we would get x plus 1 as a perfect square. But remember, we have to subtract 1 from the same side of the equation to make sure that it's still balanced. Therefore, this would simplify into y is equal to x plus 1 squared minus 2. Now, we know that the vertex will be negative 1, comma, negative 2. So let's go ahead and start graphing. Negative 1, negative 2, right here. Okay, now that we have a vertex, we just need another point to help us graph it. Let's use x equals 1 as a simple number. We get that y is equal to 1 plus 2 minus 1. And we get the nice whole number of y is equal to 2. So therefore we have the point 1, 2. And knowing the rules of a parabola, this same point will be reflected on the other side of the vertex. So we have a distance of 2 over and a distance of 4. So if we do that same on the other side, we get the point negative 3, comma 2. And here we can complete our lovely parabola. Maybe a little bit more of a pointy vertex than it should have. Now let's go ahead and graph our second equation, which is y is equal to negative x plus 3 squared minus 1. So once again, using this vertex form, we know that the vertex will be negative 3, comma, negative 1. And graphing that, we get this point right here. Let's go ahead and find another value to help us graph this parabola. We can use x is equal to negative 1. Here we will get y is equal to negative 1 plus 3 squared minus 1, which, after you simplify it all, is equal to negative 4 minus 1, which is equal to negative 5. So we have this lovely point, negative 1, comma, negative 5. Let's point down here, and once again, if we reflect it onto the other side, we get the point negative 5, negative 5. And here we have our second parabola. But look at that, they don't intersect. Finally, after all that work, we can see that this quadratic system doesn't have a solution. If the graph does not intersect, that simply means that there are 0 solutions. So therefore, we can simply conclude that there are no solutions and be done with this system. So let's wrap up this lesson. What did we learn? We learned what a nonlinear quadratic system is. A set of 2 or more equations that share variables where at least one of the equations is nonlinear. We roughly learned how to graph a nonlinear quadratic system. We also learned how to solve a quadratic system containing a line and a circle substitution, and we were able to check quadratic systems for solutions through graphing. Thanks for learning with me, and until next time!